Okay, so we have been doing these heating curves where we move along the heating curve and we're just changing states of matter. Again, this curve is not for chemical changes. Whatever substance we're working with, we're maintaining that substance's identity. So if it's water the whole time, no matter what we do to it, whether we make it hot or cold or melt it, it's just water. So this is the energy involved when you're trying to change states of matter. Turn water from ice to liquid, turn water from liquid to gas, evaporating, okay? And we've learned all the different equations that are associated with the different parts of this curve, okay? And so far, if you've paid attention, we've only gone uphill. We've gone from lower to higher, which means all of those processes are endothermic. In order to go from a lower temperature to a higher temperature, you have to put in heat. If you're adding heat, the process is endothermic, okay? So what we haven't done yet are exothermic processes, okay? So
I got a question. Was like number 16 on the homework, it's like exothermic?
I'm not sure right now. I can check in a little bit, okay?
Okay.
Okay. So now that we have done endothermic problems, we're going to do a practice with 2 exothermic problems. So the thing, and I had mentioned this last time, is that we're going to use the same equations. They're just going to come out a little bit different. So we have this question. It says, how much energy, and for right now, energy is the letter Q. That's our word for energy or heat, all right? Right now, we are only talking about energy in the form of heat, okay? Are there other forms of energy besides heat? Yes, there are, but right now, we're focusing on heat energy. So, okay, so this is Q, all right? And I give you 54 grams, so that's mass of water. And then I give you a temperature and another temperature. So basically I have delta T. Remember the triangle, it's called delta. It's the Greek symbol for delta, means change. Final temperature minus initial temperature. That's what the triangle means. And now you go, okay, I do have an equation when temperature changes. It's this. Oops. Q equals mc delta T. Okay, but we need to plot this, and then you go, so I'm trying to find Q, which means I hope I have all 3 of these. Remember, this C, this specific heat, is a constant. You will look it up. You do not have to memorize it whatsoever, all right? So I'm going to go ahead and I'm going to draw my chart. So first thing you do is draw your axes, up, down. Remember, the y-axis is where we have, so we go diagonal, across, diagonal, across, diagonal. 1, 2, 3.
I can't see that.
Okay. Now we're back to water in this problem. So this flat part right here is the melting or freezing point, okay? And for water, that's 0 degrees Celsius. And then this flat part right here, that's its boiling point. And for water, it's 100 degrees Celsius. Okay? Now, when we go back to the problem, we are starting at 20 degrees Celsius. So at 20 degrees Celsius, that's actually pretty close to room temperature. So water is going to be a liquid, right? If you have water and I hand it to you at 20 degrees Celsius. So that's my first point. And so I'm going to draw it right here-ish, right? 20-ish is between 0 and 100, like, I don't know, 20 degrees Celsius. Okay? And then notice it said ice at 0. So we talked a lot about the terminology. What does that mean, ice at 0? Well, when you think of ice at 0, you should think solid, right? So the 0 has 2 options. You have this point you could choose or this point you could choose at 0. Well, if you're going to be ice at 0, you want to be closer to the solid end, right? This is solid down here below 0. So this is where my final dot is going to go. Okay? So let's draw our arrows. You notice that our arrows are now going down the hill. So we started right here at 20, so it goes down the hill and then backwards. Okay? So I have 2 arrows. So that means I will have 2 equations. Okay, so what's this first equation right here? Well, this is a changing temperature equation, right? So it's MCAT. So this equation right here would be Q equals MC liquid delta T, right? Because we're in the liquid state right here. That's my first equation, is equation number 1. Okay, now this equation right here is Q equals NH. That's because that line is flat. There is no temperature change, so I can't use the one with temperature change. Okay, now be careful. For phase changes, there's 2 different types of H's. There's this one, H of fusion, and there's this one, H of vaporization. Fusion means melting, vaporization means evaporating. This right here, solid to liquid, or liquid, it's going to be liquid to solid, which we'll talk about in a second, is fusion down here. The vaporization one would be right here in this flat part, and that's not where we are. So now we're going to take all of our information and combine it. So I'll do equation number 1, mass. I don't remember what the mass was. 54 grams. So this is equation number 1. So I'll do, let's try to do it in a bright color. 54 grams. That's mass. Okay. Specific heat of liquid water. Again, this is a constant. So if you go back here, you look it up, it's right here. 4.184 joules over grams degrees Celsius. So here's C. 4.184 joules over grams degrees Celsius. C. Okay. Be very careful with the delta T. Where does that arrow end? Final temperature. Well, this arrow, right, ends right here. Right here is 0. Minus, where did the arrow start? 20 degrees Celsius. So yes, your temperature will come out negative. This whole term will come out negative. Okay? So our Celsius cancel and our grams cancel, and we're left with joules. Okay, so this is equation 1. Let's go ahead, I'll just calculate it out right now. 54 times 4.184 times negative 20. And it is negative 0.72 joules. Okay? So equation 1. There really isn't much difference except for you've got to be careful with the temperature when you're going downhill. Okay? Now, we need to do equation 2. So I'm going to do that down here. So that's this equation right here. So Q equals N. Now, what does N stand for? N stands for moles. And I didn't give you moles. I gave you grams. Okay, so 54 grams of water, and water is 18.02 grams per 1 mole. This gives us moles, N. This entire term is N. And then H fusion. So I go look that up. So you go back to your constants, and the enthalpy of fusion for water is 6.01 kilojoules per mole. So 6.01 kilojoules per mole. What's nice about this is that helps cancel out my moles, right? I don't see moles up here, I only see joules. So now my moles are gone. And I have the option. I either change this number up here to kilojoules or change this one to joules. They just have to both be in the same unit if you're going to add them together. I'm going to choose to change equation number 2 to joules. And the conversion factor between kilojoules and joules is 1 kilojoule is 1,000 joules. So 54 divided by 18.02. Okay, now, so this number comes out to be 18, this is a very big number, 009.9889. Okay, now we have to be careful. I will give you a hint, or kind of like something to remember. Every single equation, however many you have, or arrows, 1 arrow, 2 arrow, 3 arrows, 4 arrows, whatever, every single one will come out to be negative. So look at my MCAT equation number 1 was negative, and then you go, well, but this one didn't come out negative. Well, I need to tell you something. Fusion means melting. When you are melting, you are going from what state of matter to what state of matter when you melt something? What to what, states of matter-wise? Are you going from gas to liquid? Liquid to gas? What are we going from? Solid to liquid, right? That's the whole point of melting. Like an ice cube is solid and then it melts and now it's liquid. That's what fusion means. In this problem, what are we doing? So let's go back.
Making a liquid into a solid.
We are turning a liquid into a solid. We're actually solidifying. We're doing the opposite of melting because we're going from here, liquid, over to solid. So what you have to do is you have to throw a negative in front of your fusion constant. You have to just do that yourself because fusion means melting and we're doing the opposite of melting, so we're going to use the opposite sign, which then makes this be negative. Okay, so now we can, so this is negative, equation 1 is negative, now equation 2 is negative, we've made it negative, now we can add them together. And I'll share it right here. Let's see. So we get this huge number. Let's do 2 sig figs, okay? So negative 23,000 joules or negative 23 kilojoules. To get joules back to kilojoules, you would divide by 1,000. So then you go, what is negative heat? What? Like, there really is no such thing as negative heat. So the whole point of this negative sign is it's descriptive.
That question, can you put it in like scientific notation?
Sure.
Just wondering that.
Absolutely. So 2.3 times 10 to the 4th. Negative. So when I say it's descriptive, they're trying to tell you where the heat is going. So if you get a negative value, you are losing heat. Heat is leaving the system. Heat is being given off. Exothermic, exiting. A negative Q or a negative H means exothermic. That is an important term, exothermic. Heat is exiting, leaving, lost, given off. And so these types of problems release heat. They lose heat. Think about it. If you take liquid water and you want to turn it into ice, you got to take the heat out of it to get it to turn into ice. You've got to remove heat, lose heat, get rid of heat. That's what can get it to be cold. The lack of heat is what makes something cold. Okay? So we're going to do one more of these exothermic type problems together, and then you're going to just spend the rest of the time practicing on the worksheet from Friday. So, number 9 is our last exothermic problem. So how much energy, Q, or heat, they could use the word heat here as well, is involved when 9 grams of water, so we're back with water still, which is nice, and water's at 120 degrees Celsius, is changed to ice at 0. Okay, so we're going to go out with a bang. So the first thing you want to do is let's draw our chart. Okay. Okay, so 120 is like up here somewhere, above 100, meaning at 120 degrees Celsius, water is a gas. It's a vapor. Okay, and now we're going to ice at 0. So that's like all the way down here. So we're taking water that's a gas and we're turning it into a solid. You better believe you have to take out a bunch of heat if you're going to turn water that's in vapor form and get it to turn into ice. So my first arrow, 4 arrows. We are going out with a bang. Okay, so let's discuss the equations for the arrows. So this one right here is Q equals mc delta T. How do I know that this is the equation for this arrow? Well, because as I move along this arrow, temperature changes, and this is the equation that has temperature change in it. Now, you got to be careful with the C constant. We're in this gas phase up here, so we're going to want to use the specific heat for water in the gas phase if we're above 100. Is there another MCAT delta T equation in this? There is, right? It's this arrow right here. Why? Because as you move down this line, temperature changes. MC liquid delta T, because between 100 and 0, water will exist as a liquid. Okay, how about our 2 flat lines? Well, this one is Q equals NH, and so is this one. This one is Q equals NH. They don't have delta T in them because temperature is not changing as you move across that line. It's a horizontal line. Now you've got to be careful which H goes where. Which enthalpy, that's what H is, goes up here. H what? vaporization, because we're dealing with liquid and gas. Down here, we're dealing with solid and liquid, so that's fusion, melting, okay? At this point now, it's plug and chug. So, let's see. I think I'm going to need a lot of space. Let's see how much I can get on here. So I'll call these equations. So it's going to be equation 1, 2, 3, 4. All right. So I'm going to do equation 1 first. The mass was, I'm sorry, let's see. Was it 9 grams, I think? Okay. So mass, 9 grams. Specific heat, so that's mass. Specific heat of water vapor, and I don't know that one, so let's see. C of the gas is 1.87. So 1.87 joules over gram degrees Celsius. Okay, so C. Now be careful with the delta T. Remember, the delta means final minus initial. The final temperature of this arrow, where does the arrow end? It ends at 100. Minus, where did the arrow start? Right here, which is 120. Okay, there's equation 1. So I'm going to toggle between screens. So I'm going to actually just do this. Okay, that's what I got for the first equation. All right, next. So, right, this is plus. All right, my second equation is NH vaporization. Well, N means moles, and I don't have moles. I have grams. So 9 grams and 18, it's water. So, right, 2 hydrogens and an oxygen. So this is N. This whole term is moles. All right, next. H of vaporization. So that's a constant. So if you go back over here, H of vaporization is 40.8 kilojoules per mole. So you'll look at grams cancel, moles cancel, and you're left with kilojoules. And my first number came out in joules. Sorry, I know that this is hard to see because I ran out of room. 1 kilojoule is 1,000 joules. Now, be careful. Vaporization is very similar to the word evaporate. What's happening when you evaporate? Liquid is going to a gas, right? If you evaporate water, it's liquid water turning into a gas. Are we evaporating right now? So we're going from gas to liquid. If you don't know what this is called, please write it down. What happens when you go from a gas to a liquid instead of a, we're going from a liquid over to a gas. A gas over to a liquid. It's the opposite of evaporating. Does anybody know what it's called? So we're actually going from gas to liquid. This is called condensation. If you didn't know that, you need to know that now. It's the opposite of evaporating or vaporization. So if we're doing the opposite process, guess what? That constant we have, this 40.8, we have to put a negative sign in front of it. Negative 40.8, because we're not evaporating, we're condensing. We're doing the opposite process. So you have to throw that in there yourself. So 9 divided by 18.02 times negative 40.8 times 1,000 will give me my answer in joules. So equation 2 is a very big number. Okay. So that was equation 2. All right. I'm going to erase some of this. So we're going to work on equation 3 right now. So 3 is mass, 9 grams. Specific heat of liquid water is a constant. I've used it so many times, I know it by heart. 4.184 joules per gram degree Celsius. Now, delta T for this is where the arrow ends, which is 0, minus where the arrow started, which was 100. So my degrees Celsius cancel, my grams cancel, and I'm left with joules. So 9 times 4.184 times negative 100. And this number comes out to be negative 3733.2 joules. And we have one more equation. Okay, and that's this one. So, plus this equation. Let's see. Moles, again. So, I'm going to maybe do this up here so I can have more space than I had last time. 9 grams of water divided by 18.02 grams per 1 mole. That's N. This whole thing gives you N. All right, enthalpy of fusion is, I'm still going to run out of room, 6.01 kilojoules per mole. But we are not fusing. We are not melting. We're going from liquid over here to solid over here. We are freezing or solidifying, which is the opposite of melting. So I'm going to put an opposite sign in front of my H constant. Oops. And then, again, I ran out of room, but I'm going to turn kilojoules into joules. 1 kilojoule is 1,000 joules. So 9 divided by 18.02 to get moles, and then our constant with a negative sign in front of it.
What's H vapor like?
What?
H vapor, and I need to know that. It's just like
40.8. So now you take all these guys and you add them together. Add all these numbers together. Combine them. Oop. I basically, if you have the kind of calculator, you can keep all the numbers in your calculator and then just add them all together. All right, what are you guys getting? Okay, so with 2 sig figs, this would be negative 27,000 joules or negative 27 kilojoules. And if you have a negative sign, that means this heat or energy is being lost, given off, removed. Exothermic. I do want to talk a little bit about, calories. It isn't done any different than what we've been doing. You just have to do a final conversion at the end. So I'm gonna look at number 9, and then I'll show you how to, for example, set up number 11. So we've been solving for Q in all of these problems, but that doesn't mean you can't solve for anybody else. As long as you have all of the variables but one, you can solve for the one that's missing. So that just involves a little bit of critical thinking. I shouldn't have to walk you through like hand by hand how to do that, but I will kind of give 2 examples before I set you free to finish this this worksheet. So for example, number 9, it says how many calories are needed, and we're changing water at its boiling point. So you go, okay, well, if you're doing this, I'll show you, for example, what this means. So you have this, right? Well, water, so this is 0, this is 100. Water at its boiling point is right here. So you're going from here to here. That's it. All you're doing is changing water at its boiling point. So your only equation is Q equals NH vaporization. That's it. So how do you do this? Well, they say calories. Well, I don't care about calories right now. Just convert to calories at the end. Do the problem just like it says. So N is moles. It was a lot of water, right? Was it 1,200 grams or something like that? 1,200 grams. Okay, so Q equals 1,200 grams of water. And I need moles, so I need to turn this into moles. 18.02 grams per mole. Okay, that gives me N. H vaporization, you can look up. It's 40.8 kilojoules per mole for water. So look, grams cancel, moles cancel, and we're left with kilojoules. If we go back to this problem, I gave you a conversion. Between calories and joules. So if I take my number and turn it to joules, I can just do one more step using that conversion factor to turn it to calories. It says 1 calorie is 4.18 instead of 4.184, whatever. It's not a big deal. So joules go on the bottom, 4.18 joules in 1 calorie. I just did an extra step to turn a joule into a calorie. It'd be like doing an extra step to turn inches into feet. You're just using a different unit of energy. Now we're in calories instead of joules. But it all starts the same as we've been doing. Get your joules, and then you can convert to calories. Okay? So again, it's just this extra step. And remember, they just said you were at its boiling point. So at its boiling point means you're at 100. You're not going up, you're not going down, so it's just one equation. Just like if they said you were at its freezing point, I guess you could go either way, forward or backward. You're just here. You're not changing temperature in any way. So it's just one equation. Okay. So that's an example of how to do one with calories. Now, let's look at what would, let's do 13. Let's see. Actually, let's look at 11. It says, what would the final temperature, temperature final, and I give you mass, and I give you energy, so this is Q, and I give you an initial temperature. All right? Now you go, okay, so far in here when I've done Q, it's come out in joules. All right? Which means you need to take the extra steps to turn your kilocalories, that's what kcal means, into joules. So you got to do a little bit of work up front. So here's what I mean. 3.60 kilocalories. First of all, let's get rid of the kilo. 1 kilocalorie is 1,000, right? Kilo means 1,000. Joules, kilojoules, grams, kilograms. The kilo itself means 1,000 calories. And then 1 calorie is 4.184 joules. Again, this is a conversion factor. And the reason I want to do this is because I want to know Q. This is what Q will be in joules. So 3.6 times 1,000, times 4.18 or 4.184, okay? I think they put 4.18. So my Q is 15,048 joules. Q equals mc delta T. So Q is right here, 15048 joules equals, do I have mass? Yes, I do. It is 250 grams. So Q, mass, you can look up the specific heat of water. It's 4.184 joules per gram degrees Celsius. I'll notice my grams will cancel. And then delta T means temperature final minus temperature initial. Well, they're asking you to solve for part of this. Like, they want to know this guy. So this is like your X, if you want to write it like that. And then they gave you an initial temperature. So again, this is just critical thinking. There's no reason you can't do this. You have all of the pieces that you need. So just because I don't show you exactly how to do every single problem does not mean you don't have the tools to do it. It's just a different rearrangement. So for T initial, I'm going to plug in what they told me it was. They told me it was 22. All right. So what can I do? I can divide both sides by these numbers right here, right? So 250 oh, sorry. I want to show you this. This will so then you divide both sides. Oop. Okay. Oh, what just happened? So this is gone. And you calculate this out right here, and you should get 14.386 something equals T final minus 22. Easy. Add 22 to both sides. And your T final is 36.4. Let's just do 36 degrees Celsius. So it started at 22 and ended at 36.4 with this much energy put in. It's just a different rearrangement. This time you have Q and you're solving for T final. They could even give you all T's, all C's, all Q's, and you could solve for mass. There's no reason you can't solve for any of the variables involved in the problem just by using algebraic manipulation. You just have to make sure you plug the variables in the correct locations.